In this video, we're going to present the proof that the satisfiability problem is NP-complete. Before we get started with this rather complex proof, let's look back and remember how we decided that, or how we proved that the post-correspondence problem was undecidable. We used a technique of reduction. Remember that we had the Turing machine acceptance problem, ATM, okay? And we knew that that was undecidable. We knew that ATM is undecidable. And we reduced the ATM problem to an instance of the post-correspondence problem. And that proved that the post-correspondence problem was undecidable. Because if we had a particular acceptance problem, we could just use our reduction to turn it into an instance of the post-correspondence problem. And if we could decide that, then we could decide the acceptance problem for Turing machines. But we knew that that was undecidable, and so therefore the post-correspondence problem was undecidable. And in doing that, we showed how to simulate the execution of a Turing machine with tiles in an instance of the post-correspondence problem. Remember how we had the computation history, which was a sequence of configurations, and we arranged to create a bunch of tiles or dominoes or for our post-correspondence problem in such a way that if you could solve the post-correspondence problem, then you had found an accepting history. So the computation history was a sequence of configurations. Each configuration described the state of the Turing machine and its tape and head position at any one point in time. And a computation history was a sequence starting from the initial configuration, hopefully to an accepting configuration. Finding a solution to the instance of the post-correspondence problem was equivalent to finding an accepting computation history. Okay, so we're going to do something similar in this proof that the satisfiability problem is NP-complete. So our goal is to prove that satisfiability can be solved in polynomial time if and only if P equals NP. And the real problem is showing that if we can find a solution for a polynomial time decider for the satisfiability problem, it proves that P equals NP. So let's look more carefully here at what NP is. A problem is in the class NP if there is a non-deterministic Turing machine that will solve it in polynomial time. So what's a problem in NP look like? Well, you could boil it down to being a non-deterministic Turing machine with an input. That's an instance of a problem in NP. You've got a non-deterministic Turing machine and you've got some input. Okay. What we're going to do is show how to convert it into an instance of the satisfiability problem. Okay. The satisfiability problem, remember, is a Boolean formula, and we're looking for an assignment of true and false to the variables in that formula that make the entire formula true. So we will convert it into an instance of the satisfiability problem. It'll be a huge Boolean formula, but it'll still be polynomial in length. Okay? And we're going to convert it into an instance of the satisfiability problem such that there's a branch in the non-deterministic computation that accepts if and only if the Boolean formula is satisfiable. Okay? So we're going to do the conversion from the non-deterministic Turing machine with its input into a satisfiability problem. And we're going to do that conversion in polynomial time, such that if you can solve the satisfiability problem in polynomial time, okay, that is, if you could solve a problem in polynomial time, then you could solve any problem in NP in polynomial time. If you've got a problem in NP, then what you've got is a non-deterministic Turing machine that runs in polynomial time and an input. That's the nature of the problem. That's what you would have if you have a problem in NP. And can you tell whether that non-deterministic Turing machine accepts that input? And can you do it in polynomial time? Well, what we're going to do is we're going to convert it to a problem. We're going to convert it into an instance of the satisfiability problem. In other words, we're going to create a huge Boolean formula, really big, but we're going to do that conversion in polynomial time. And if you could solve that Boolean formula, if you could find an assignment of truth values to it in polynomial time, then you would know whether that non-deterministic Turing machine would accept that input or not. And you would know that within polynomial time. So that's the general strategy of the proof. Let me restate this theorem. The theorem is that the satisfiability problem is NP-complete, sometimes called the Cook-Levin theorem. And it says that any problem in NP can be reduced into a satisfiability problem. And we could do that reduction in polynomial time. So if you could solve the satisfiability problem in polynomial time on a deterministic machine, then you can solve any problem in NP on a deterministic Turing machine in polynomial time. That is, P equals NP. So here we go with the construction. Given a problem in NP, okay, we're going to convert it into a Boolean formula. Well, given a problem in NP means we've got a non-deterministic Turing machine, which we'll call N, and an input to that Turing machine, which we'll call W. So we are given N and we're given W. And we're going to have to convert it into a Boolean formula, phi, in such a way that phi is satisfiable if and only if that non-deterministic Turing machine accepts W. What that means is N has an accepting computation history for W. So if N accepts W, then the Boolean formula is satisfiable, and if the Boolean formula is satisfiable, then N accepts W. Okay, the length of our input W is characterized by little n. Big N is the non-deterministic Turing machine. The accepting computation history in the non-deterministic Turing machine N can take at most polynomial steps, or n to the k steps for some k. How big is the tape going to be on that accepting history? Well, at most, with n to the k steps, we can use at most n to the k tape cells. So our tape size is limited to n to the k tape cells. So what we're going to do is imagine creating what we call a tableau. This is an array, and on the next slide I have a picture of it. And this table, if you will, is going to be big. Okay, it's going to be n to the k times n to the k cells big. Each cell in the table will, we'll talk about that in a second, but the size of this table is n to the k times n to the k. So here this n is the small n for the size of W. And this table is going to model the accepting computation history. It's a gigantic table, it's big, but it's still polynomial in size. Now, we're going to imagine this table, and what we're going to do is we're going to create a lot of Boolean variables to model what this table could look like. This table is filled with cells, and the cells may contain something or something else. And what we're going to do is we're going to create variables, Boolean variables, to model what could be potentially in each cell of this big table. And then we're going to create a formula to express all the constraints on this table and the values in the cells of this table to guarantee that the table will model a legal accepting computation history. So we're going to create a formula to express some constraints on the values that we could store in this table. And this set of constraints will guarantee that this table will model a legal accepting computation history. Okay, so here's a picture of this gigantic table. It has n to the k rows. I haven't shown them all. And it has n to the k columns. So it's an n by k times n to the k array of cells. And each cell can contain either a pound sign, a state, or a symbol from the tape alphabet. Each row in the table corresponds to a configuration of the tape. And so we can see the first row shows the initial configuration in a computation history. We're starting in Q0, the initial state of the Turing machine, and initially the first N cells of the tape contain the input W. So we have those, and then the remaining cells of the tape are blank. Now remember, we said we won't need any more than n to the k cells. So because this computation is polynomial, we're only looking at one branch in the non-deterministic history of computation, and in any one branch we'll have at most a polynomial number of steps. So at most, starting at the left end of the tape, we can, if we move to the right on every transition, we can only go a polynomial number of cells out to the right. So we can't change any more cells than that. So we need n to the k cells for our tape, plus we're going to have a pound sign to mark the end of the tape, and we're going to have a pound sign to mark the left end of the tape, plus we have to have a single cell to hold our state. And so we need n to the k plus 3, really. And we won't need any more tape than that to perform a computation that takes no more than n to the k steps. So again, our table is going to model an accepting computation history. And we would like to know whether an accepting computation history exists. And the question is, can we find out whether an accepting computation history exists in polynomial time or not? And so we ask whether there is such a table. Okay? And we want to note that every cell in this table will contain a single symbol. Okay? It can contain a pound sign, which we just used to mark the leftmost column and the rightmost column. We won't see pound signs anywhere else. And every row in this table will contain a configuration, which consists of the contents of the tape plus the current state. And the current state will be embedded somewhere in this row. The initial configuration will have the state being the initial state, and it'll be at the very left end of the tape, indicating that the head is on the first symbol of the input. So each cell contains a single symbol, and each cell can contain either a pound sign, the state, and every row should have exactly one state in it embedded somewhere, and the remaining thing that the cells can contain is a tape symbol. So we could specify that Q times gamma times the pound sign. Now, what could be in each cell? Well, we can ask what's in some particular cell, like the cell 5 down and 8 across might contain a 0. Let's just assume that our tape alphabet is zeros and ones. It might also be a blank or pound sign or some state. Now, we're not actually constructing the table itself. What we're doing is we want to know whether the table exists or not. Okay, that's our question. Does an accepting computation history exist? So that's the same question as, does a table exist that is a valid computation history? And what we're going to do is we're going to construct constraints that describe what the table should look like if it does exist. So for every cell, such as the cell 5, 8, we're going to create several Boolean variables to describe that state. And so for the cell 5, 8, we'll need a number of different variables. The cell could contain a 0, or it could contain a 1, or it could contain a blank, or it could contain a pound, or it could contain a state. And here I'm showing Q4, but our Turing machine will have other states as well, maybe a bunch of states. So for each one of these possibilities, we're creating a new Boolean variable. Only one of these should be true because the cell should have exactly one symbol in it. So for example, if the cell contains a 1, then the variable x581 would be true, and the variables x580 would be false, 58 blank would be false, 58 pound would be false, and so on for the other variables, for the other tape alphabet symbols and states. So we can use this notation for our variables. These are the variables in the Boolean formula that we're going to be creating. X sub I, J, S. I and J range between 1 and into the K. Plus 3, I suppose, to be very accurate. And S ranges over the possible states, such as Q4 and Q0 and so on, the symbols of this tape alphabet, and also this pound sign. So we have these numbers are all fixed. The sizes of these set S's of Q and gamma are fixed, and these are polynomials. So we can see that we have a polynomial number of variables. Now remember, we're not actually building the table. What we're building is a formula, a Boolean formula, and we want to make this formula, we want to construct this formula in such a way that it has a bunch of constraints. The formula will express constraints on the table, and so what we're doing is we're building a formula that has a lot of constraints that make sure the table is a legal computation history that ends with except. So we're going to build a logical formula such that if it's satisfiable, if we can satisfy those constraints, then it means that a table exists, and that table describes a legal computation history. So when we build a formula, the formula will essentially contain a bunch of constraints. In fact, we can look at 4 different kinds of constraints. And any combination of assignments to the variables that satisfies all these constraints will indicate that there isn't a table that could exist that describes an accepting history. So if the formula can be satisfied, then it means the constraints can be met, and that means that a table can exist, and that means that an accepting history exists. So let's look at the 4 different kinds of constraints. The first constraint is that every cell contains exactly one symbol. Okay, I said previously that we had several different variables for each cell, and exactly one of them was true. So we need to express that as constraints. Every cell contains exactly one symbol means effectively that only one of these variables is true. Remember, I talked about the variables that describe cell 5, 8, and we have similar variables for all the other cells, but only one of these can be true because the cell can contain only one symbol, and exactly one of them must be true. So those are constraints of the first type. And then we have constraints of the second type that specify that the first row is a starting configuration, namely that we're starting in the initial state of the Turing machine, Q0, and W occurs at the first part of the tape. The next part of the tape is all blanks. So that is these are constraints on the first row. And then we have the third sort of constraint, which is that there's an accepting, that this is an accepting configuration. An accepting computation history. In other words, some cell contains the symbol Q accept. So somewhere during the computation we reach the accept state. And finally, we need the constraints that basically indicate that each row which expresses a configuration can legally follow the row above it according to the transitions of the non-deterministic Turing machine we're modeling. So let me say that again. Constraints of the fourth type make sure that we have a sequence of configurations and that each configuration legally follows the previous configuration. That the relationship between one row and the row that follows it indicates that that configuration can lead to the second configuration according to the rules of the non-deterministic Turing machine that we're trying to model. And so this formula that we're trying to build, all in all we call it phi, and we'll make it from these parts. So that we have phi cell, phi start, phi accept, and finally phi move. So phi cell is the constraint that every cell contains exactly one symbol. Phi start is the set of constraints that the first row is a starting configuration. Phi accept is the constraint that some cell contains the accept state. And phi move is the constraint that every configuration legally follows the previous configuration according to the rules of the Turing machine. The entire formula phi is just a combination or a conjunction of the different constraints that I mentioned before. So as we describe the formula phi, we're going to describe all of its parts: phi cell, phi start, phi accept, and phi move. And these are all conjoined together with the logical and symbol. This formula, phi, is going to be really huge, but it's going to be polynomial in the size of the input w. And let's just kind of remember where we're going. If this Boolean formula has a solution, then it means that there exists an accepting computation history for the non-deterministic Turing machine. And if there is an accepting computation history, then this formula has a solution. So if you can determine whether this gigantic formula phi has a solution, and you can determine that in polynomial time, then it means you can determine in polynomial time whether a non-deterministic Turing machine will accept w. So given a non-deterministic Turing machine w and an input string, that is, given a problem in P, we can convert it into this formula phi. And if we can determine whether that has a solution, and we can make that determination in polynomial time, it means we can determine whether there is an accepting computation history for the non-deterministic Turing machine, and we can do that in polynomial time. And so that would prove then that P equals NP. So if we can prove that we can solve the satisfiability problem in polynomial time, it implies that P equals NP. So all we have left to do in this proof is to show how to construct this Boolean formula phi. Remember that this Boolean formula contains a number of pieces, which I call cell, start, accept, and move. And each of these pieces together describes what it means for a table to be legal. If you can find a solution for the Boolean expression, that means a table exists, that is a legal table. And each one of these pieces of phi describes what is required of a table for it to be a legal description of a computation history. Remember and I'm going to go through it, this Boolean equation, and show what it looks like in more detail. It's a gigantic long thing. Although it's polynomial in length, it's still quite long. It's not exponential in length, it's only polynomial in length, but it's still pretty big. And I'm going to sketch it out, and I'm going to break it down into pieces. Each one of these pieces is a constraint. The first piece is the constraint that every cell in the table contains exactly one symbol. Because of the way we're representing cells of the table, we need to put some stuff into the equation in order to make sure that every cell contains exactly one symbol. The second piece, phi sub start, is the constraint that the first row, the top row of the table, contains a valid starting configuration. Phi sub accept is the constraint that the configuration reaches an accept state. And finally, phi sub move is that every line, every row in the configuration table, table is a legal configuration that follows from the previous configuration. In other words, this constraint specifies that each configuration legally follows from the previous configuration according to the rules of the Turing machine's transition function. So on each slide, on the next couple slides, I'll look at one of these pieces, but they're all conjoined together with the and sign. So let's start off with the first one. Remember how we're representing the information about what the table contains. We've got a number of variables. For every cell, for example, for cell 5-8, we have several variables, one for every possible symbol in the tape alphabet, as well as the states and the pound sign. Each of these is a different variable, and each can be true or false independently. And if a variable is true, for example, if the variable x sub 5 sub 8 pound sign is true, it means that that cell contains a pound sign. On the other hand, if this variable instead is true, it means the cell contains a Q4. Both of these things shouldn't be true at the same time because the cell should contain only one symbol, and likewise all of the cells should contain something. So first of all, here's the constraint that at least one of the variables describing this cell is true. So for any given ij and subscript s, where s is either a state or tape symbol or the pound sign, then one of those, at least one, is true, and that's by this gigantic OR. So remember our notation. This is like a summation notation with a big sigma, and you have an index written underneath it that ranges. And in our case, the index is S, okay, and it ranges over all the possible symbols that the cell could contain. It could contain tape symbols, it could contain state symbols, or it could contain the pound sign. So this is essentially all of the variables x in the equation are involved in this. Well, yeah. And so for a given I and j. Now, for a given I and j, every cell should contain only one symbol. And we can express that differently. For every pair of variables for this particular cell, at least one of them must be false. We can't have two of them that are true. Okay, that would mean the cell contained two symbols at the same time. So for every symbol S, and again S ranges over this stuff here, I didn't write that down, but for every S and T also ranges over this set, and for every S and T that are not equal, we add an additional constraint, so this is conjoined together, that either one's false or the other's false. It's possible they're both false, but this is a not X and this or not X, so at least one of them has to be false. Combining these two pieces, okay, with a and sign, exactly one variable has to be true for the cell, and that's what we want to express by these two pieces. So we're going to combine this one and this piece with an and we also need to do that for all cells, okay, for all ij. So this piece of our big equation, here's our big equation here, is a statement that's true of each and every cell. So here I'm letting j and k range between 1 and n to the k. Actually, our table is to be more correct and more precise, our table is a little bit bigger than n to the k because we have the pound signs and we have to have room for the state. So really this thing ought to say n to the k plus 3, but I think you get the idea here. So this we make a statement about every cell. And what do we say? Well, here's the part that says at least, the cell contains at least one symbol, okay? And here's the part that says that the cell contains at most one symbol. So this is saying for all cells I and j, for all cells I, comma j, the cell contains exactly one symbol. So that's our first constraint. Next, we'll look at the second constraint as part of our big Boolean formula to describe a legal table. And that constraint says that the first row must describe the initial configuration. And basically, this part of the equation is just a bunch of things anded together. First of all, here's our table down here, and the initial row of it, here's the top of the table, and this top row has to have a pound sign here. So we're just saying that x 1, 1, pound is true. And we need to have a pound sign here. This is really, I guess, well, so here we're saying that. And this column is really 2 to the n plus 3, but I've just put 2 to the n here. And so we're saying that there has to be a pound sign there. And also we have to start in the initial state, Q0. And so this cell of the table has to contain Q0, and that's expressed by this. Now the next part of this piece is that the input string should occur at the beginning of the tape, and the rest of the tape should be all blanks. So the input string occurring at the beginning of the tape, well, our input string has n characters in it, and we've used W for the input string, so the pieces of that are W1, W2, and Wn. So in the third cell, 1, 3, we need W1. Okay, in the next cell, 1, 4, we need the second symbol from the input string, which is little w2. And in the third cell, and so on all the way up to this cell, which is n plus 2. It should contain the last symbol of the input. And then, so that's the constraint that W is in the first n cells of the tape. And the last thing we need for this initial configuration is that the remainder of the tape is all blank. So starting with cell n plus 3, the one that was directly after this one, the blank must be turned on, or in other words, the variable that says it contains a blank must be true, and so on for the remaining cells all the way out to the last. Oh, should this be into the k plus 3 maybe? Yeah, but in any case, all the way out to the, oh no, into the k plus 2. All of those should be containing blanks. Here's our third constraint, which says that the except state has to be reached in the computation history. This is basically just saying that some configuration somewhere has to have the except state in it. And so this one's a pretty easy constraint to express with a Boolean formula. Some cell somewhere contains the symbol for the except state. So we're saying that for all cells in the table, one of them has to indicate that that cell contains the except state. So a gigantic disjunction. Okay, the final constraint in our equation is that every configuration can legally follow the previous configuration according to the details of the Turing machine's transition function. Now this is a non-deterministic Turing machine, so I say can legally follow. There can be several possible next configurations from any given configuration. All we care about is that a row in the table is legal in the sense that it is one of the possibilities that can follow the previous row. Each row describes a configuration, and we want to make sure that given one row, the row directly after it is possible. It's a legal configuration that could be reached by following one of the transitions in the non-deterministic Turing machine's transition function. So here's kind of a sketch of how we'll look at this. Here is just one transition in the non-deterministic Turing machine's transition function. And this is an example. And in this case, we're going from one state to another state. In this example, Q7 to Q8. And we're reading a symbol, and we're writing a symbol, and in this case, we're moving to the right. So what can we say the table is going to look like if one row follows another row legally? Well, the area around the tape head is going to look like this. The rest of the tape, we're not sure quite what it's going to look like, but it's basically going to be exactly the same. The top and bottom are going to be exactly the same. So here we're saying that we move from state Q7 to Q8, okay, and we move to the right. And there has to be, if there is a B in this row, and we are in Q7, okay, in other words, we're in state Q7 positioned on a B, then this is one of the transitions we might take. So a row that contains these characters below it is legal. It's a legal possible successor configuration. We've moved to Q8, we've replaced the B with an A, and I've also drawn in another character here. There might be a C, some other characters, those are just copied. Okay, we're going to look at a sort of a window of 3 by 2, so I wanted to include C here as well. Because when we move to the left, we see C, no pun intended. So here's the same transition, only we're moving to the left this time. And we're starting off again with the same configuration, or at least this portion of the configuration that we're looking at is the same. And this time we're moving to the left. So we need C here because not only do we change B to an A, but we move C, or we don't really move C, we move our tape head. So in the configuration, the symbol that was showing the state will become the symbol that shows the tape cell that contains C. Okay, so in some sense, C does move to the other side of the tape head. And note that C is not mentioned in these transitions. So regardless of what C is, these transitions are legal. So these can apply for any symbol C that is on the tape. So notice kind of what we're doing here. In both cases, we're looking at a state Q. We're in some state. In this example, it's Q7, and we're looking at an area of the tape that contains the characters to the left and right of that state, and then the characters that change below it can be any of these three characters. In this case, in both cases, the symbol over here changes, and in this case, the symbol over here changes, and in both cases, this symbol changes. So we're sort of, if we can center ourselves on this cell right here, okay, we'll call that one the cell ij for now, and the transition function tells us what is legal to find in the cell surrounding cell ij. So we'll call that a window that's centered on cell ij. And there are lots of these windows all over the table, but for this configuration to legally follow this one, we have certain constraints about what might appear in this, and that's determined by the transition function. If we have these two transitions, then we know that these two pictures are okay. Any table that contains a window that's centered on Q7 that looks like either this or this would be okay. It's not clear which transition we took, okay? This is not deterministic, so it's either one of these could have been legal transitions, legal ways to get to Q8, and perhaps it would have been interesting if I'd drawn this arrow just from this Q7 to this Q8 rather than repeat the states to emphasize that it is non-deterministic. either one of these could follow. So in any legal computation, the window that's centered on this cell Q, that contains Q7 could look like this, or it could look like this for any symbol C. Okay, so now let's look at this again. Here's one of our transitions. I've repeated it, and this is the one that moves to the right. And remember, I said this is true for any symbol C. Okay, so here's what I drew on the previous slide with Q7 changing to Q8, and I just used C to indicate that it could be any symbol in the tape alphabet. Let's assume that our tape alphabet has maybe 4 symbols. I'll just use A, B, C, and D. And we also have the blank symbol. So we need to create these windows. Okay? If there was an A here, then there better be an A here. If there was a B to the left of the state, then there better be a B down here, or a C, or a D. And I'll include the blank here too. So for each one of these windows could have been a legal window in a table. If we take this transition, it doesn't really matter what character was to the left of the tape head, as long as it's copied down correctly and appears to be the same character below. So for each one of these could describe that transition. So for each transition, we have a number of possible windows, and each one of these windows can be described. So let's look at this one right here, where it's a B that's copied down. And just to describe this window, we can make a formula. Okay? And what this says that, well, I've kind of drawn 6 variables here, and I've used these dotted lines to show how they correspond to the squares. So this variable here, ij, describes the center of the window, okay, and it says that it better contain the Q7. And here we have ij minus 1, ij plus 1, so we're describing this cell, and that cell. And here we have I plus 1, j minus 1, I plus 1j, and I plus 1j plus 1, so we're describing that cell, and that cell. And so we're saying that this one should contain a B, and this one, and then it should contain a B here. This cell in the configuration directly following should also contain a B. The cell that contains a Q7 had better contain an A in the following row that describes the next configuration. And the cell that contains B now contains Q8. And so for every transition, there are a number of these windows. And for and there may be, many transitions in the non-deterministic Turing machine. So we have lots of valid windows. So I'm just going to label this one, this one right here is window 37, or W37, not to be confused with the input string. So given any position in the table, it must match one of the legal windows. Okay? So there may be, as I said, there may be, 100 different rules, and for each rule there may be 5 or 6 different transitions. So maybe we have a total of, and for each one of those there may be a number of different variations based on the tape alphabet. So we could get lots and lots of windows, maybe 592. I just use that as an arbitrary number. So every position in the table, every ij position, must match one of the legal windows. So it must match window 37, or window 38, or window 39, and so we can express that with a disjunction. So for every ij position, the table must contain or match one of the legal windows centered on that position. So finally, we get to our formula, the part of the formula that describes the constraints of the moving of the transition function. And we need to put a constraint on every single cell in the table. This is every single window. So I and j, we have to have some stuff for every possible I and j. So we let I and j range between 1 and into the k. Okay, so we have a lot of terms here, all ANDed together. And then for each one of those possible window positions, we have a possible it has to match one of the windows. So that's this big OR right here. Okay? So ranging over all of the possible window combinations, maybe there are 592 of them, we have a disjunction centered on that I and J. And then within each one of them, we have something that looks like this that describes the window. So it has 1, 2, 3, 4, 5, 6 positions. So that describes the constraint that says that each configuration must legally follow the previous configuration. Okay, so all in all, we've got all of the pieces to our Boolean formula, and this more or less completes our proof. Okay? If this thing can be satisfied, if we can find an assignment of trues and falses to all those variables that satisfies this gigantic equation, it's gigantic, but it's still polynomial with respect to the size of the input string. If we can find a set of values for those Boolean variables that satisfies this formula, then we know there is a table that we can build that describes an accepting computation history. And if there's an accepting computation history, we know the Turing machine, the non-deterministic Turing machine, accepts that string. And if we can, so we can build this formula in polynomial time, given a non-deterministic Turing machine. In other words, given the Turing machine, we can build a formula and we can do it in polynomial time. If we can then solve the polynomial time, the formula in polynomial time, we can determine whether there's an accepting computation for that non-deterministic Turing machine in polynomial time. Okay? And so this is the proof. This ends the proof that the satisfiability problem is NP complete. If we can solve the satisfiability problem in polynomial time, then we can solve any problem in NP in polynomial time.